This video is about if the Earth is rotating, why do we humans not get flung off? I think I'll get a little bit into also why the water of the Earth doesn't get flung off or clouds. So, okay. Now remember the rotation of Earth. I don't have anything. I guess I'll just use. Okay, I'll use this. Actually, I think okay. So so the Earth rotates. Does anyone know how fast the Earth rotates? Could think about that. How fast does the Earth rotate? The answer is so obvious. You know exactly how fast it rotates. It rotates 360 degrees every 24 hours, right? Where is the position of the sun in the sky? How long will it take for it to get to that position? So if I take this and I rotate this all the way like that, and then I just do that, but complete that in 24 hours. How slow is that? That is like so slow. So why would you be getting flung off something that's going so slow, right? That's your first. It's the first thing that doesn't make sense. Now, because the Earth is so big at the equator, it might only be going that slow because it's so far, it's going really fast. But remember, if it's so big, once the circle becomes so big, you're pretty much traveling a straight line when you're only going such a small distance. It's pretty much straight. There's such a slow curve. The curve of the Earth is 1 inch down every 1 mile. That's really small, a small curve. So you're mostly traveling one direction. So the change in that direction is actually really small. So you are going faster. Now, the science, the research that I've done, I've seen a lot of other people doing research, so it's either accurate or it's not, but there is a consensus. It's 0.5%, so I'm gonna weigh 0.5% less at the equator, because I'm gonna be spinning, and I'm gonna want to be going away. There's gonna be a centrifugal force, and I will weigh a little bit less. This is observable. You can even go on a mountain with the same effect because you're further away from the center. You're gonna weigh less. At the equator, you're gonna weigh less than at the North Pole. These are measurable. You can measure this. And how else does this not make sense? Except for a predicted formula that we have, a predictive formula. We can predict that you would weigh less at the equator based on, the Earth rotating in centripetal and centrifugal forces. So that is why we are not getting flung off, because we're not going fast enough. That's the reason, that's the numbers. So you would have to prove that wrong. We have all the evidence. Now, why isn't water getting flung off? For the same reason that we aren't getting flung off. There's not that much of a centrifugal force to fly us off. And I did see a video also too, like if you have a scale video of if you have a globe, like a typical globe that's 2 feet in diameter. So, that's about like that big. I'm like moving all right, so yeah. Okay. And so the amount of water, right, that would fill all our oceans would be like, if you had like about that much water. So if you had oh boy, that's got, you could say it would be 1/4 cup of water, probably less. So you could pour 1/4 cup of water around that 2-foot globe, and that's how the water represents. So relative to the mass of Earth is so massive that it's just a little bit of water compared to the mass of Earth. Okay, if you can just imagine 1/2 cup of water, pouring that on a 2-foot diameter globe, it's not going to be taking up a lot of the surface. Is going to be really low. And so that's proportional to the Earth. So it's easy to keep all that water on, especially when it's not that much of a force. So the spinning does not make that much force. The gravity is what's the biggest one, and that's why the moon can affect the tides, but the spin doesn't. The Earth does have a bulge, the centers, and that's because of that spin. So it wants to go out, so it just bulges just a little bit. So you can measure that, and you have to put that in the calculation for the equator. It's about, like, I think it was 0.4% for the speed, plus 0.1% for the distance, because you have a bulge at the equator, so you're further away from the center, so you weigh even less, just by a little bit. So that is how Earth's rotation makes sense. It's going really slow, and it's going fast at the equator, but that only accounts to a small amount of what you're feeling. You're not changing direction that much. So that is why you don't feel the effects. I did have some questions about that, because I did think we were going really fast, and from my understanding, we were at 1,000 miles an hour at the equator. You're changing 22.3 million feet, per second of a change, so like you're falling down with the Earth. Like that's like a lot. So maybe I mess up the calculation, but because how much distance you would travel if you're traveling 100 miles per hour, you travel that many miles in an hour, or sorry, it was 1,000. So if you're changing 8 inches per mile, you would be changing, so yeah, a lot different. So it'd be 8 times 8,000 inches. So see how many feet. That's why inches to feet. I'm looking it up right now. We're gonna do inches to feet, but it put, all right, so let's, I'm sorry, so it's inches to feet. Google does not want to work it. All right. It's not helping me out. Okay, good. Now we finally have it. So 8,000 inches. 2, 3. So about exactly about, you're about 700 feet per hour. And then you could divide 8,000 by 60. Sorry, give me a second. So you have 8,000. Divided by 60, so each minute you're going down 133 feet. Or you could say divided by another 60. No. Divided by 60. I know this is a long video. So you're at 2.2 feet per second of a drop. So I guess I was 2.3 million. I was way off, but it looked like it was about, the zeros were off. So anyway, 2.2 feet per second. So that's not like a big drop. That makes a lot more sense. So now my calculation numbers are agreeing with the science numbers that I was seeing with the consensus. And yeah, so that is why you don't feel the effect of the Earth rotating as much. Or you do feel it, it's not a big feeling. It's a 0.5% at the equators. That spin is not acting, it's not that big of a force. So there you go. That was a big question that I got.